Actually, if you want to do it with the velocities, then there is another method.
Hang on.
Okay. All right.
Should probably make sure to keep this u negative. Minus 50 times 1 or 10 times 1, so minus 10. So v when it hits the ground is minus 60. So then how do we find this final velocity? Usually that would be done by like v equals u plus at equals u plus at, or v equals u squared plus 2as, but because we don't have an s value necessarily, doesn't really help all that much.
Correct.
Wait, if we know a final velocity, then and we know what the acceleration as a result of gravity is, then doesn't that tell us the time taken to reach that point? Or
yes, that will.
Yeah.
But you don't know the final
Because
velocity.
well, I mean, we can calculate the final velocity as v equals u plus at between c and b. So then that gives us the final velocity of 60. But even still, we know the velocity at point C. And the thing is that the time taken to get to point C will also show as the acceleration on top of the initial velocity. And because it was dropped, the initial velocity must be 0. So given that at point C, the object has u equaling negative 50, it should mean that it has been 5 seconds since it was dropped. So the time taken between point A and B should be 6 seconds. I don't care. Pick one.
Okay, I'll explain both the methods. You'll enjoy both the methods actually. See, S is equals to ut plus half AD square. What is the, if I'm going from A to B, S will be minus H is equals to 0 minus 5t square. So you can say H is equals to 5t square. Okay. Similarly, I can apply the same thing for A to C. So that is minus H dash is equals to minus 5 into t minus 1 the whole square. So you can say H dash is equals to 5 into t minus 1 the whole square. You have H and you have H dash and you have H minus H dash, which is equals to 45. Okay. And that is equals to 5t square minus 5 into t minus 1 the whole square. That is equal to 45. When you solve this equation.
Wait, hang on. Where are you deriving these expressions for?
Okay. You know this.
Oh, hang on. You're using that equation because u has to be 0.
Yes.
Because it was dropped from standstill. 1/2 5 minus h. That's why, well, I mean, height's a scalar quantity, so who cares about negative, positive? Minus 5t squared. Okay, that makes sense. So then h prime is 5 of t times t minus 1 the whole square. Okay, this is definitely requiring more algebraic usage. And
no, then I'll teach you another method. Okay. You said you were doing with the velocity. Then in that case, in fact, I'll quickly draw the graph. Okay. Starting from 0, I'm drawing speed versus time. Speed versus time. Okay. Now, this is up to t minus 1. This is t minus 1. And this is t. Okay. This is t. Yeah. So this is, let's say u. Okay, I'll write v1 in fact. U is 0 we are considering. So this is v1 and this is v2. Okay, we know one thing, that this particular area, what is this area? This area is 45.
Yeah. Oh, if you think about it as a graph, it makes it a little bit simpler.
V1 is equals to, V1 will be equals to 10 into t minus 1. V2 will be equals to 10t. Okay, we are considering the speed. Yeah. So that means this is equal to 10 into t minus 1. And this is equal to 10t. Okay. Use the area of trapezium. Okay. And this difference is 1 second.
Yep.
Okay. Now when you do this, half into sum of parallel sides, that is 10t plus 10t minus 10.
It therefore solves for
into
t
1.
because everything is in terms of t.
Okay, so
Yep.
so you do get what is this? 20t
t minus 10.
20t minus 10, that is equals to 90. So 10
The whole
goes
thing's
there.
over 2 though.
So
The
t is
whole
equals
thing's
to
over
5
2.
seconds.
With actually, it's all over 2 because it's multiplied by 1/2, right? So then theoretically it should be 10t minus 5. Because it's multiplied by 1/2.
Yeah,
above
so if you're writing 10t minus 5, then that will be equal to 45, and then 5 will go on the other side, so 50. So 10t
Oh.
equals to 50, so t equals to 5.
Yeah, fair enough. Sorry, I wasn't.
So see, the thing is, so like it can be done with the speed as well as with the formula, with the graph as well as with the algebra. Okay, all right. So okay, so this is the thing that we have in the motion under gravity. In fact, I have given you like all the difficult questions. Easy questions, I'm sure you are able to do, okay, easily. Okay, but like these are some tricky questions, and I believe that like you understand what should be the approach. Okay, whenever you get any questions about the motion, you need to think what you are given, what has been asked. Okay, and then apply
Yeah.
the right Stewart equation. Okay, it's very, very important to choose the right Stewart equation. Okay, and then
Okay.
execute it. If you are blank, go with the graph. Okay, you getting it?
Yep.
Always graph always works. Always. Okay.
Okay.
Right. Okay, so we'll stop here. And if you have any worksheet from your school, then it's fine. Which I'm sure like you do have the summer
Sorry.
work, I guess.
Yeah. Before we like completely finish up, could you just explain to me how, like, at a very fundamental level, how to go about calculating normal forces for ramps? Because I actually never did that. So
Calculate what? Moment of force.
normal forces for ramps. For
Oh,
inclines.
okay, on inclines.
Normal
Alright,
forces
see,
on
I
inclined
got
planes.
it. I got it. I got it. So there is something called free body diagram. I'll teach you that thing quickly.
Yep. Yep. We did free body diagram in class. It's
The school goes
decently.
very fast, and they go insanely fast. Okay, your school. So
Yep.
I want you to do one more session with me, but you need to give me time, man. Like I want some
Yeah.
time from you. Okay, all right, anyways,
Yeah.
so let's talk about the free body diagram over here. See, the thing is, whenever you're drawing the free body diagram, you need to think of the 4 forces first of all. Okay,
Right.
first force that you need to think of is the weight always vertically down. Okay, always.
Okay.
W is equals to mg, which is always vertically downward. There is another thing called tension. Tension is always along the stretched string. It is always along the stretched string. That means if the string is like this, the tension is like this. Okay, but if the
Okay.
string is like this, the weight is vertically downward. Okay, if the
Yep.
string is like this, still the weight is vertically downward only. Okay, if the string
Yep.
is vertically like this, the tension is along the string. The third force
Yep.
that you are supposed to know is the normal force. Normal force is the contact force. It is possible only
Yeah.
if the object is in contact with the surface. Okay, and it is
Yep.
always perpendicular to the surface. The word normal means perpendicular. So if
Yep.
you have a block like this, so this block actually applies a force on
Force
the
to the ground,
surface.
and the ground applies a force to it.
Exactly, upward, right? So this is known
Yep.
as the normal reaction. Now suppose
Yep.
if the object is like this, and because of certain force, it is applying the force on the surface like this, then in that case the normal reaction will be in this direction.
That's normal. Yep.
Okay, don't ever think that the normal reaction is always upward. No,
Yeah.
not like that. If suppose you are having
Reactive force.
yeah, if you are having an
It's like the same
inclined
thing
plane,
as being on. It's the same thing as being on the equator. It's
yes,
based on the frame of reference. It's a normal force,
absolutely.
even no matter how you look at it.
Now the next thing that we have, and the final thing that we need to know, is the friction. What is friction? Friction is basically the
So-
force which is opposing the motion with respect to the surface. Okay.
I
Friction
think we get into
Fr
that this unit.
is equals to mu times R. Mu is a constant and
Yep.
R is the normal reaction. Okay.
There's
Yeah, this is
static
the
and reactive friction, right?
kinetic and static friction basically. Yeah. So
Okay.
yeah. Now I'll give you some rules for the free body diagram. There are some rules.
Free body diagram. I think we've gone over this. I should probably either find the notes or recall from memory. Things I best recall from memory are one, forces project or force vectors as shown in free body diagrams project outwards from the free body. The free body, generally the center of mass, is used as the point of application for forces. And the other, the more important thing is that forces are generally drawn according to some sort of scale that has to do with their magnitude and direction.
Absolutely. So all these things are basically the rules for the vectors. Okay.
Yep.
For the free body diagram, there are some very specified rules. Let's understand that, okay, quickly. So suppose like I have an object on this particular inclined plane, okay, and so how will I draw the, and this is, let's say, theta, angle theta, okay. So how will I draw the free body diagram for this particular object? So first rule is basically draw the two axes, okay.
Yep.
Draw two axes with the center of gravity as origin. Okay. Yeah. Now the two axes which you're drawing, one should be along the line of motion, and another one perpendicular to the line of motion. What is that?
Yep.
So basically what I'll be doing is
I don't know.
yes, absolutely. Yes. Yes, so here this is the center of gravity. Yeah, what you have drawn is correct. So like this and this. So basically we have these two axes. Okay, this is the
Yep.
very first step. Then the second step is draw the forces which I mentioned earlier. Okay, the four forces which I mentioned. Okay, whichever is applicable. So draw all forces. So quickly draw all the forces. So there is weight. I spoke about the weight. I spoke about the tension. There is no string, no tension. Then there is, so if suppose the motion is in this direction, so let's consider that the friction is in this direction. Okay.
Yeah.
So this is the frictional force, and there will be some normal reaction, that is R. Okay. Now the third rule which you need to follow is the forces which are not along the axis need to be resolved. Forces not along the axis are resolved. Okay, resolution means you need to get the component of those forces along the axis. Okay, so let's resolve the forces. So we have this particular force.
So the only real force that, yeah, that's the only force that needs to be calculated into two components along the axes.
Yes. So this is mg cos theta, and this one is mg
sin theta.
So we got all of them. And then the final rule, fourth rule, is if it is in equilibrium. If in equilibrium, then the net force is equal to 0. And if in motion, if we're moving with acceleration a, then ma is equals to the driving force minus opposing force. Let's say that it is not in equilibrium and it is going in this particular direction with a. Okay, so how the equation will look like over here? The equation will be ma. This is the net force, ma, will be equal to the driving force. In this case, the driving force is mg sin theta, which is pulling it down.
Yep.
Okay, minus the opposing force is fr. Okay, and that is the frictional force, which is mu r.
Yeah.
So mu times r. Now this r will be equal to the action force, which is mg cos theta. Okay, clear?
Okay.
Yeah. So there are some variations also.
And then mu is going to be coefficient of friction, right? Coefficient of friction.
Absolutely. Absolutely.
Okay.
There are 6 variations of this thing that we have in IB, HL. Okay. So let's do one class where we'll be learning all the 6 variations. Okay. And then if we'll be having more time, then we'll go back to the projectile motion. We are done with the motion under gravity. We'll do the projectile motion if we have more time.
Okay.
When can we do the class?